Welcome all of you. In the last few lectures, we have been trying to build the essential mathematical background that is required for us to study electric and magnetic phenomena. Today what I propose to do is to start the discussion of electrostatics, beginning with the Coulomb law. However, before I do that, it's a nice juncture for us to actually recall and summarize all the important results that we have obtained so far. I should tell you that it is not that we have built all the required mathematical apparatus. We have built the essential mathematical apparatus, and whatever is required for later use will be developed as we proceed when we discuss electric and magnetic phenomena. I started with the notion of a coordinate system and established the properties of three important coordinate systems. The first one is rectangular Cartesian coordinate system. Rectangular Cartesian coordinate system, which is as ever described in terms of three orthogonal coordinates bases, which we denoted by the x-axis, the y-axis and the z-axis with the unit vectors in the respective directions. This is the simplest of the coordinate systems, and then we went on to generalize this to discuss the properties of what I called as cylindrical coordinate system. Sometimes it is also called cylindrical polar coordinate system. Then we went on to discuss a slightly more complicated example, but a very useful concept, and that is of spherical polar coordinates. Spherical polar coordinates. All these three coordinate systems are very important for us, and therefore I would urge you to solve as many problems as you can in making a transformation of the vectors and the scalars from one coordinate system to another. After having done that, I went on to discuss two very important concepts, namely that of a scalar field and a vector field. As I told you, scalar field occurs in the form of the scalar potential, whose gradient is given by the electric field, and the vector fields occur because the electric and magnetic field themselves are vector fields. After having introduced these two fields, which we will be dealing with throughout the course, I introduced three very important operations, and they are the following. The first one is the gradient, which when acting on a scalar field produces a vector field. So what do I mean by that? If you give me a scalar field f, which is a function of r, then I operate the gradient on it to get a vector field, which I shall denote by v f of r. This is a vector field generated by the scalar field by the action of the gradient. Next, I introduced the concept of a divergence. So what does it tell you? The divergence allows you to construct a scalar field given a vector field by acting as an inner product. So what do we do now? You give me a vector field, any arbitrary vector field. I am going to dot it in the sense of a vector inner product, and that produces a scalar field, which I shall denote by f of v of r. This is a scalar field generated by v. The last important concept that I introduced was that of a curl. So what does the curl tell you? Curl allows us you to construct one vector field given another vector field. So how shall we denote that? We now take the cross product of this gradient operator, the del operator, and then with the vector field, and what do we get? We get yet another vector field, which I shall denote as v prime of v of r. This vector field v prime is generated by the original vector field v. All these three are very important, and we spent considerable time discussing the physical meaning, the geometric meaning of each of these quantities. The gradient f tells you the direction and magnitude of the slope at that particular point. Divergence tells you whether or not there are sources for the field at that particular point, and the curl tells you whether there is a certain rotation or a curliness associated with the vector field. At this point, it is also good for us to remember that when I construct the curl of a vector field, I have two classes of vector fields. Either I have a polar vector field or an axial vector field. When the curl operates on a polar vector field, it gives me an axial vector field, and when it acts on an axial vector field, it gives me the polar vector field. That is something that we have to remember. At some stage we will introduce what is called as a vector potential, which is a polar vector field. When the curl operates on it, what do I get? I get the magnetic field, which is an axial vector. On the other hand, when I operate curl on the magnetic field itself, then what do I get? I get the current density, and the current density is a polar vector field. So curl has the property of changing the nature of the vector field with respect to coordinate inversion or reflection. That is something that we have to remember. Having done that, we now move on to recapitulate all the important theorems that we stated involving the divergence, involving the curl, and involving the gradient. These are indeed very, very important, and they were developed together as electrodynamics developed in the 17th and 18th centuries. In fact, people invented these theorems in order to understand the electrodynamic phenomena. Therefore, it is worthwhile spending some time, although we have spent several lectures discussing that. The first one involves the gradient. Suppose I have a scalar field f and I construct a vector field by operating gradient on this. Now, let me take a coordinate system here, and let me say that I have a point P1 and a point P2. The point P1 is denoted by x1, y1, z1. These are the coordinates for the point P1. x2, y2, z2 are the coordinates for the point P2. I now wish to move from the point P1 to P2 in any manner whatsoever. Remember, I have chosen these 2 points arbitrarily, and all over this space I have defined the scalar field f. Of course, once I operate the gradient on it, I have a vector field. Now suppose I take a path like this, which I shall denote by C1. I may take yet another path which goes like this, which I shall denote by C2. I am moving from P1 to P2. I can take yet another path which actually curls like this and comes back and terminates at P2. What I can do is evaluate this gradient f along this particular path as I move from the point P1 to the point P2. How do I do that? I take the gradient and dot it with the line element dl, which is defined along this particular curve. So what do? I dot it and I integrate from the point P1 and P2. As it stands, it appears that this equation is meaningless because I have written so many curves here. I have a C1 here, I have a C2 here, I have a C3 here. I can make as complicated a curve as I want. Therefore, I should also specify the curve along which I am going to integrate. So in order to do that, I shall put a symbol C here. So I am integrating the gradient f dot dl along a particular curve C from a point P1 to P2. C could be C1 or C2 or C3 or any other curve that we want. Now, the remarkable result is that this object is simply given by the difference of the scalar field f between P1 and P2. So how do I do that? This is a scalar object, notice. I will simply write it as f of P2 minus f of P1. Of course, if you want to express this in terms of the coordinates, because I erected a coordinate system here, I will write it as f of x2, y2, z2 minus f of x1, y1, z1. In other words, what we have is the path independence of this particular scalar field. So for example, if I were to start with this point P1 and P2, the simplest way to integrate this might be actually draw a straight line and integrate along with this and not make any complications of integrating over very, very involved and convoluted curves. That is the statement. This is not an unfamiliar result for you, because even in mechanics you studied this when you introduce the concept of a potential, and you know in a conservative force field the work done is independent of the path that is taken. That is what this summarizes. And eventually we are going to write the electric field in terms of the gradient of a scalar potential, as I told you. That is possible when the charges are static, when there is no current which is varying with time, or there is no magnetic field which is varying in time. In that case, it collapses to the examples that you have worked out in your mechanics, and this has an obvious physical meaning. It doesn't matter how you move from a point P1 to P2, the work done is the same. It is simply the difference between the energies associated with the point P2 and associated with the point P1. So that is what we have in this particular result. I have not proved this result. You must have proved that in your mechanics course. But anyway, please go back and recapitulate this, because that is something that we are going to use again and again. We shall now move on to state two more theorems involving the divergence and the curl. That is something that you are not familiar with your mechanics course, because there you do not deal with fields. So I spent quite some time discussing them. Now let me summarize them by stating the results. What I now do is to consider a vector field V, and now I consider not the integral of this V with respect to the dl, but I take its divergence. Remember, the divergence of the vector field is a scalar field. What do I do with this divergence? I shall now integrate it over a certain volume. So I will write it as a certain volume d cubed r, which will be indicated by the symbol V here. Okay. So in order to avoid ambiguities, I will make it a curly V here, and this is the volume element. Now when I say that there is a certain volume element, so this is a certain region in space, this is my volume over which I am going to integrate, and notice this volume is obviously bounded by a surface S. So here I have a volume V, which is the interior of the region which is bounded by the surface S. Now obviously what I am going to state is the celebrated Gauss divergence theorem. So what does it say? This tells you that this volume integral, which is a three-dimensional integral, where I am going to sum over divergence V over all infinitesimal volumes and add them up, is simply given by a surface integral. So I write the surface here and write V dot ds. That is what I do. Now I have employed this notation circle around this integral to remind you, to emphasize that this surface is a bounded surface. It is not an open surface. Any volume in any given region is bounded by a surface, and that surface is obviously not an open surface. It is a closed surface. Imagine a balloon, for example. As you keep on blowing it, at some points you might even like to press it. There is always a certain volume which is bounded by the surface, namely the balloon itself. So what we are saying is that give me a vector field V. What you can do is to integrate over the whole volume, or equivalently the divergence, obviously you can integrate over whole volume, or equivalently simply take the vector field, do not bother to evaluate its divergence, dot it with the surface element and integrate over the surface, and that is what you are going to get. Please remember, when I write this ds, I always mean the outward normal at every given point. That is a convention, and we should not violate that. This is the famous Gauss divergence theorem, which we shall use to the fullest extent in studying electrostatics. The last result which I would like to recapitulate is what is called as Stokes theorem. So what does Stokes theorem tell you? Stokes theorem allows us to write a surface integral as a line integral. That is the beauty of that, and obviously it will involve the curl. So again I will consider a vector field V denoted in this particular fashion. Now what we shall do is to construct another vector field by operating curl on this. What shall I do now? I shall now integrate it not over a line, not over a volume, but over an open surface. Let me make it precise. So I am going to integrate it as an open surface, and I will write it as a ds. So what do I mean by an open surface? A very simple way of imagining is to imagine this to be a certain loop or the boundary of a membrane. This is a line, a curve C. This curve C is enclosing this particular membrane which I am shading. It is a two-dimensional surface formed by the boundary which is this curve. What I can now do is to take this membrane and stretch it out, or stretch it in, or distort it in any way I want. Whatever I might do, I am generating an open surface. It is open because it is bounded by this curve C. Now I can make this curve C smaller and smaller and smaller, and in the limit that the curve C reduces to a point, it has no extension at all, then it becomes a closed surface. In that case it will be enclosing a volume, but that is not what I am doing. I will always keep the curve C, and it shall be finite, however small it may be. And we are going to evaluate the curl V at every point on the surface, and we do the surface integral. Stokes theorem tells you that this operation is equivalent to, it can be replaced by a line integral which can be written as integral V dot dl. Obviously, what bounds an open surface is a closed curve. It cannot be an open curve. Therefore, in order to emphasize that, what I will do is I will put a circle here and I will put a C here. These indeed are very, very important theorems for us, which is the reason why this result goes by the name of Gauss, who was one of the greatest mathematicians. He is called the prince among the mathematicians, and this result goes by the name of Stokes. The same Stokes who studied viscosity to a great extent. These are the results that we need. Please remember that these are very, very important theorems, and you should work out as many examples as you can. Having done this, it is now time for us to really study the Coulomb law. What I will first do is to state the law, as you are all familiar with. Then I will look at each of these terms, try to understand their physical significance, what their meaning is, what their physical import is, and what the current understanding of these objects are. Coulomb introduced it sometime in 16th or the 17th century. Today we are in the 21st century, therefore it is good to ask what is it that we know about the charges starting from the time of Coulomb. So let us start with that. All of you are familiar that suppose I am given two bodies. So let me call this as body A and let me call this as a body B. Now let us say that this body has a mass m1 and this body has a mass m2. Now what I wish to say is that apart from possessing a mass, it can also possess another attribute, another quality, another quantity called the charge, which I shall denote by Q1 here and Q2 here. These charges are produced, for example, by rubbing amber against silk. These are the first experiments. And on a dry winter evening or a winter day, if you are wearing synthetic clothes and if you walk on a carpet, you know that you pick up enormous amount of static charge. We are all familiar with this. If you are wearing a woolen sweater and if you are walking on a carpet, you pick up so much charge that if you try to remove your sweater, you will see the crackling sound that comes. Sometimes you might even see sparks. So much of charge is there that it given discharge. This is precisely the origin of the word electricity. Okay? So intuitively, by experience, although we do not know how to describe it quantitatively at this particular point, we know there is some object called charge, and I am going to denote that quantity of charge by Q1 for the object A and Q2 for the object B. At this point, we know that object A will have a certain size, object B will have a certain size, object A will have a certain shape, object B will have a certain shape. We shall ignore them. What we shall do is to assume that these are far apart. So what do I mean by that? If I were to draw these lines and denote the distance d, now let me blow this up. So suppose this object has a size like this, this object has a size like this, let us say. Now let me say that the maximum point to point distance, the maximum distance between one point on A to one point on B is denoted by some r1, and similarly it is denoted by r2. We are making a statement that d is much greater than r1, d is much greater than r2. So if I say that d is much greater than r1, this distance between A and B is much greater than r2, we can ignore to the first order the fact that A has a size, it has a shape, B has a shape, it has a size. In that case, the only relevant parameter, the only relevant distance k is given by the quantity d, which measures the average distance between the body A and the body B. That is something that we have to remember. Otherwise, Coulomb's law is not easy to state. Later, actually, we are going to spend time discussing what happens if the finite extension of A is taken into account, the precise shape of A is taken into account, the finite extension of B is taken into account, the precise shape of B is taken into account. That will give rise to what we call as a dipole field, quadrupole field, so on and so forth. So, in order to be precise, in order to know exactly what we mean when we say something, we shall say that we are ignoring the size and the shape of the bodies A and B. In fact, that is precisely what Coulomb did when he did the experiments. If you did that, the force of interaction between A and B is given by the following result. Now, in order to be even more careful, let me ask what is the force exerted by the body B on the body A. Therefore, since I am employing the notation 1 and 2, what I shall do is to write F2 acting on 1. If you want to write, you can even say B acting on A. Force is a vector quantity, so let me put a vector sign over that. So what am I saying? I am saying that I am interested in finding out the force exerted by the body B on the body A. So if I want to do that, this object is given by the Coulomb law, which tells you that F is nothing but 1 over 4 pi epsilon naught. This comes because of a very peculiar choice of units about which I will have to say something at a later stage. But right now let us accept this. Then I have the charge q1, then I have the charge q2, then I have the distance d squared, and in which direction is that? It is in the direction from B to A. So what shall I do about that? This is what the direction. So at this particular point, since I have not erected a coordinate system, if I denote this with the unit vector hat d hat, I will write it as a d hat. I am measuring the direction from B to A. Of course, there is a reciprocity, and what does reciprocity tell you? If I am interested in the force acting on the charge 2 by charge 1, 1 over 4 pi epsilon naught remains, q1 remains, q2 remains, d squared remains, d will be replaced by minus d. In that case, the magnitude of the force is the same, but we shall now act from the direction of A to B. That is what Coulomb law says. In making this, I should be a little bit nitpicking at this particular point, although it is not often emphasized. When I say that I want to measure the force acted upon by B on A, actually I should imagine that B is a very, very massive object. Strictly speaking, if I take two charges and put them together, A is going to act on B, B is going to act on A. As I told you, F1 acting on 2 is nothing but minus F2 acting on 1. That is what I said, D will be replaced by minus D. Therefore, there is nobody to stop from 1 acting on 2 as much as 2 is acting on 1. However, if I just want to measure the force acted upon by 2 as an action on 1, I should ensure that B shall not move. That is very important. The forces are the same, it is not under our control because the charges q1 and q2 have been given. The only way we can control is to ensure that these masses are different. So what do I mean by saying that? Let me make it more precise. If I am interested in measuring F2 going to 1, I will make M2 much greater than M1, so that in the first approximation, in the 0th order, I can take M2 to be infinitely heavy. In that case, F12 is of course equal to minus F21, but the acceleration suffered by the body named 2 is so small that we can ignore its motion, and therefore only the body A sees the force acted on it by B. So if M2 is much greater than M1, I can write this object relation to be M1A in the Newtonian approximation. I can calculate the acceleration A and verify the Coulomb result. In a similar manner, if I want to find out what is the force on B because of A, so I am interested in this on B because of A, what do? I will go to the opposite result, limit M1 much greater than M2. Then what happens? If F21 is what I shall write, F1 going to 2 will now be given by M1 A prime, let us say. I can measure the acceleration A prime and I can verify Coulomb law. There is one more point of care that we have to take. It is not simply a statement of a formula when it comes to Coulomb law, because it is a fundamental law of electrodynamics, and that is the following. Suppose I consider the action of B on A and A starts moving in some particular fashion. Now, if I really want to measure Coulomb law, I should ensure that the velocity suffered by A, the change in the velocity of A should be very small. So what do I mean by that? This acceleration should be small. That is very important. If we forget that, then we will not be able to verify Coulomb law. In fact, the best way to verify Coulomb law is through the so-called null experiments. So let us say that this A is attached to a spring. So let me denote it in the next page. Let us say I have the body A, I have the body B. So B is a very massive object. So I say M2 is much greater than M1, and then there is this A. This carries a charge Q1, this carries a charge Q2. The distance between them is D. I want to find the force acting on A. What shall I do? What I shall do is to connect it to a spring and leave it here instead of letting it move. Now, really speaking, the spring should be in this direction. So let me draw it here because it is along the line joining the two charges. Okay. So let me say that it is rigidly held at this particular point so that it cannot move vertically. Now, because of the force, what happens? Q1 moves either in this direction or in this direction. In which direction it moves depends on the relative sign of Q1 and Q2, to which I will come in a minute. What happens? There is going to be either a compression or an elongation of the spring, and we know all about the laws of the spring. F is simply given by minus kx. If I take this to be the x-axis, so the force of compression or elongation, depending on whether the force is attractive or repulsive, will exactly balance the Coulomb force. Then we have a null experiment which causes a displacement but no acceleration in the final stage. So we gave an operational definition of measuring the force between two abstract quantities called charges, which we have not yet quantified. In this lecture, I am not going to work out any problem or state any results. Most of the time will be spent merely on analyzing the meaning of each of these terms. So therefore, let me return to the Coulomb law again. Let me write it down. F Coulomb is given by Q1 Q2 by R squared R hat. That is what I am writing. The meaning of these objects is clear. For sake of units, I should introduce this quantity 1 over 4 pi epsilon naught. What we shall now do is to stare at this expression and ask, is there anything familiar that looks like this? And the answer is obviously yes, because this expression bears an uncanny resemblance to yet another very, very well known law, which you have studied in great detail in your dynamics course, in your mechanics course. And what is that? Gravitational force, which tells you that this is nothing but G mm by R squared R hat. I should be careful, I will put a minus sign here to emphasize that gravitational force is always attractive. Appearances are deceptive. By looking at this, we might feel that, oh, Coulomb law is no different, no more complicated, or no less complicated than the gravitational law, and universal law of gravitation is enormously successful. We can understand the tides, we can understand the falling apple, we can understand the motion of the moon around the earth, we can understand the motion of the sun around earth around the sun, and so on and so forth. So maybe all that we have to do is go back, revise whatever we learnt in mechanics, come back and repeat those exercises using the Coulomb law, because all the mathematical techniques should be the same, because the laws are different. All that I have done is to replace G by 1 over 4 pi epsilon naught, capital M by let us say Q1, small m by let us say Q2, and R squared is there, R hat is there. But as I told you, the appearances are deceptive because there are also lots and lots of dissimilarities, which makes electromagnetism very, very different from gravitation. Whereas gravitation binds the planetary system, it holds a galaxy together, it holds clusters of galaxies together. Electrodynamics cannot do that. We cannot imagine electrostatic force holding the earth and the moon. But on the other hand, electromagnetism holds a molecule together, it holds an atom together, it holds clusters of molecules together, which cannot be accomplished by what? It cannot be accomplished by a gravitational force. And therefore we should ask, what is it that makes electrodynamics so very different from gravitational phenomena, although the laws appear to be the same? And these are indeed deep issues. Therefore let us spend some time trying to appreciate what they really mean. The first point of departure is in the very nature of Q. I put a sign minus here. What does it mean? I said that it is always an attractive force, which is the reason why we always say masses are always positive. So for the time being, let me say that I will call these masses as gravitational charges in analogy with what? In analogy with the electrostatic charges. What is the property of the gravitational charge? Gravitational charges are always attractive. So they all belong to one single species. That is what it says. So let me write it in big words. Gravitational force is always attractive. So let me write them in big words. Gravitation is always, to be underlined, attractive. And here the electrostatic charges, in contrast to the gravitational charges, behave differently. How do they behave differently? Let us ask that. In order to look at that, what I shall do is to collect a large number of charges. So I have a body 1, 2, 3, 4, etc. carrying a charge Q1, Q2, Q3, etc. I have a large number of charges. So I have a bag of charges, if you feel like. Now what I shall do is to take them pairwise and start measuring the force by making use of Coulomb law. So what shall I do? Let me take Q1 and Q2 first and measure the force between Q1 and Q2. I am not interested in whether Q1 is acting on Q2 or Q2 is acting on Q1. I ask whether this force is attractive or repulsive. That is, whether the two charges tend to move towards each other or tend to move away from each other. I shall employ a notation. I will say that if Q1 and Q2 tend to move towards each other, I will employ the sign minus, because the distance between them starts decreasing. If the charges tend to move away from each other, I shall denote it by the sign plus. I can make a table. Now let me look at, for example, f of Q1 and Q3. It might so happen that they tend to move towards each other or they tend to move away from each other. That is, either it can be repulsive or attractive. So let us say Q1 and Q3 move away from each other, and I shall denote it by plus. Now a good question to ask is, what would happen if I consider the charges Q2 and Q3? What is it that I can say about that? Mind you, I am telling you that Q1 and Q2 are attracting each other, Q1 and Q3 are repelling each other. Now it turns out that if I look at the interaction between Q2 and Q3, it is always attractive. This is a universal law and that is contained in the Coulomb law. So what are we saying? We are saying that there are two species of charges. So there is one species of charge, if I put them together, they all repel among themselves, they repel each other. Then there is another species of charges also which also repel each other. But to pick up one element from a species A, another charge from a species B, they will attract each other. So the best way to summarize them by employing this particular notation is to say that some charges are positive, some charges are negative. So what do I mean by that? I will say that charges come in two species. So I will denote them by two sets. So there will be, let us say, Q1, Q5, Q6 in this particular example, and S2 is given by Q2, Q3, Q4. Let us look at that. What do I mean by saying that the charges come in two species? Every element in S1 is going to get repelled by the other fellow. Q1 is repelled by Q5, Q1 is repelled by Q6, Q5 is repelled by Q6. Every element in S2 is repelled by another charge in its own same set. Q2 and Q3 repel each other, Q3 and Q4 repel each other, Q2 and Q4 repel each other. But pick up any charge from the set S2, pick up any charge from the set S1. So let us say I pick up charge Q3 from S2, I pick up the charge Q5 from S1, Q3 and Q5 are going to attract each other. That is the statement when we say that charges come in two different species. So we need a convention in order to distinguish these two species. Therefore, by this time you should be familiar, you should be sort of striking all of you that this is nothing but the combination, the multiplication of numbers plus 1 and minus 1. Plus 1 into plus 1 is plus 1, minus 1 into minus 1 is plus 1, and plus into minus is minus. Therefore, arbitrarily, by choosing some convention, we shall say that one of the sets has positive charges, the other set has negative charges. So let us say all charges Q belong to S1 are positive and all charges belong to set S2 are negative. This is a convention that we need to employ, and what we now do is to say that the charge carried by a fundamental particle, the electron, is negative, whereas the charge carried by yet another fundamental particle, the proton, is positive. That is the convention that we are going to employ. So charges come in two different species, unlike masses which are always attractive. There is no concept of a repulsion between two different masses and therefore signs of the masses. This is not the end of the story. There is yet another very, very deep difference between the charges and the mass, for which we have to remember a little bit of relativity, the special theory of relativity. In Newtonian mechanics, we know that mass is independent of speed. That is what Mr. Newton said. Nothing wrong in this because this is an excellent approximation when the speeds of the objects are very, very small. However, even if you people have not studied relativity, all of you are familiar with the result, with the fact that mass changes with speed. This is the famous Einsteinian result. In fact, suppose an object is at rest and this is a mass m naught. So I shall denote it by rest mass. Suppose it starts moving with a certain speed v. So now I ask, what is the mass when it starts moving with a speed v? What is the formula that we have? That is simply given by m naught divided by root of 1 minus v squared by c squared, where c is the speed of light. So you can easily see that when v equal to 0, it is nothing but the rest mass. But as v approaches c, the denominator goes to 0 and the mass goes to infinity. The inertia becomes very, very large. In other words, the mass of an object is not independent of the state of its motion. That is very, very important for us to know. And it actually goes to infinity. Of course, if you have a very, very small velocity, you can make a binomial expansion and you can write it as m naught into 1 plus half v squared by c squared. C is an enormous number, 3 into 10 to the power of 8 meters per second. Even the earth, which is going around the sun with an enormous speed, 30 kilometers per second, is nothing compared to the speed of light. Is that okay? Therefore, in the zeroth approximation, it is nothing but m. But if you go to large speeds, very, very large velocities, m is certainly going to change. What happens when it comes to charge? So let us imagine that there is a certain body A having a certain speed v moving in some given direction. It might be in a gravitational force, or it might be attracted by a certain law which is given by Hooke's law, in which case not only does it have an velocity, it also has an acceleration a. If the force is time dependent or it keeps on changing from point to point, in general the acceleration is a function of time and so is v a function of time. Now this body has a mass m, by that I mean the rest mass m, and it has a charge q, by that I mean the rest charge q, because I have to be very careful now. We now ask the question, what happens to this charge q when this object suffers a change in its state of motion? It starts moving with a certain speed which keeps on changing with time. The remarkable fact about the charge is that, what I am going to write now, the charge is independent of the state of motion. The object may be at rest, it might be hurling very fast towards something, it might be going round and round the way the electron goes around the hydrogen in the proton in the hydrogen atom, whatever it might be, its charge is something that is going to remain absolute. In that sense, charges are really like numbers which add up. You don't have to worry about anything else. This is something which is glossed over, but this is the most important fact that distinguishes electrodynamics from the gravitational law, from the ordinary mass. Therefore, it is worthwhile asking, what is the experimental evidence for this statement that charge is independent of the state of motion? Today we have very, very great experimental evidence coming from accelerator physics, to which I will come in a short while. But even with your knowledge of Bohr model, it is actually possible to get a hint. This is not a rigorous kind of argument that I am going to give, but a very good hint, a very good intuitive feeling as to why charge must be independent of the state of motion. In order to do that, let us recall Bohr model. So what does Bohr model tell you? Bohr model tells you that there is a very massive object called the proton, which is sitting at the center, and then there is an electron which is going around in a circular orbit. Of course, this is what is going to happen even classically, even if you did not have Bohr model, except that the orbit need not be circular, it can also be elliptical. But Bohr considered circular orbits, that is what you have studied, let us stick to that. The difference is that Bohr is going to impose a condition on the angular momentum carried by the electron. Since it is a circular orbit, let us say that the radius is r, what do I do? What I do is to first of all identify the force of electrostatic attraction with an equivalent centrifugal force. So what should I do? I will write mv squared by r is simply nothing but 1 over 4 pi epsilon naught q electron q proton divided by r squared. This is an attractive centripetal force. So what are we saying? We are saying that the electrostatic force of attraction, which is on the right hand side, is equivalent to a centripetal force. Many times you read that this is a centrifugal force which is balancing the electrostatic force. Please do not commit such a mistake. All that we are doing is to identify this physical force 1 over 4 pi epsilon naught QE QP by r squared with a equivalent centripetal force which is also attractive. That is what we shall write. This is common to both Newtonian approach or the classical approach and the Bohr model approach. The real Bohr model departure is in quantizing the angular momentum. So what does it say next? The angular momentum is simply given by mvr, the product of velocity into radius into mass. Since it is in a circular orbit, I don't have to worry about writing cross products and all that. All of you know the meaning of this. This is simply given by nh bar, where h bar is the famous Planck constant. Now, this forces only certain values of the radius for the electron. In an ordinary classical situation, depending on the initial energy and the initial angular momentum, the electron can have any radius that it wants, but this condition, which is called as the quantization condition, forces only certain values of the radius. So, we shall put Vn, Rn to emphasize that. So, it is a matter of very simple substitution now. What do? Take this, you have mv squared by r, eliminate v or Vn into Rn in this particular expression and try to get an expression for the radius, try to get an expression for the velocity. Obviously, the minimum energy will be there when n is equal to 1. So, put n equal to 1 and find the expression for the velocity. If you did that, I am not going to work that out. I will leave it as an assignment for you. You should certainly go and work it out. It turns out that the speed with which the electron goes around the proton is of the order of 2.2 into 10 to the power of 6 meters per second. This is indeed an enormous speed. Remember, I told you that the earth goes around the sun with a speed of 30 kilometers per second. Here we are speaking of 2.2 into 10 to the power of 6 kilometers per second, which is 2 orders of magnitude, 100 times larger than whatever the speed of the earth is. Whatever you see terrestrially is of course very small compared to the speed of earth around the sun. Therefore, you can almost forget about all these objects, projectiles, missiles, rockets, whatever it might be. So, this is what we have. But this speed is still small compared to the speed of light, because c is given by 3 into 10 to the power of 8 meters per second. That is what we have. Now, what I shall do is to consider not the electron going around the proton, but imagine applying Bohr model for a very heavy nucleus. So, let us say z is equal to 100. So, when I wrote this expression, I wrote the charge of the electron, charge of the proton. That means there was only one charge sitting, that is the hydrogen atom that I had. But suppose I replace this proton by a nucleus. All of you know from your 12th standard, the nucleus comes with as much charge as there are protons. Is that okay? And that atomic number is denoted by the symbol Z. In that case, the charge carried by the nucleus is given by Z QP. Therefore, I will put a Z here. So, all that I need to do is to take over the expression for the energy, for the forces that I wrote for the hydrogen atom, and multiply it by Z. The electron is still moving in a circular orbit. In fact, if I want to be very careful, I can put a E here and a V here to emphasize that this is for the electron. Now I ask, what is the change in the speed of the electron when I say that I look at a Z which is much larger than the proton. So what do I mean? Let us say that I take Z is roughly 100. That is what I am going to look at. If you did that, you can easily verify that this expression also gets the multiplicative factor Z. So what happens? So now I can write VE for Z equal to 100 is simply multiplying the original fellow by 100, which is equal to 2.2 into 10 to the power of 8 meters per second, which is sort of precariously close, which is dangerously close to the number 3 into 10 to the power of 8 meters per second. I have to be very careful when I am making this statement. If you get too close to the speed of light, you cannot use non-relativistic mechanics. Getting the expression mvn or mv squared by r equal to 1 over 4 pi epsilon naught qu qp by r squared, that might be wrong. It doesn't matter. It still gives us a hint as to how the speed changes. The mass changes by an enormous quantity. Never mind. You look at a nucleus which has Z is equal to 100, or lead which is Z is equal to 80, which is quite close to 100, and look at the hydrogen atom. Both the atoms are what? Both the atoms are actually completely neutral. So, what do I wish to say? Consider hydrogen atom. You have Z equal to 1 and a single electron. Consider a heavy nucleus. For example, it could be uranium, which has some to a mass number equal to 230 and atomic number very close to Z. So, consider an atom which is close to Z is equal to 100. So, what is it that happens there? I have 100 electrons. These 100 electrons are going to move with different speeds according to Bohr. The innermost electron is going to move with a speed which is very close to speed that of light. However, it doesn't matter. This atom and this atom are both electrically neutral. How could they remain electrically neutral? They could remain electrically neutral because although the charges are going to move with different speeds, although the speed of the charges depends on the orbit in which they are sitting and also on the value of Z, the charge itself does not change, and therefore both of them remain electrically neutral, and thus we have shown, we have argued, we have hinted at the fact that the charge of an object is independent of the state of the motion. That is what we have shown. In fact, one could go one step ahead and ask, what is the force of interaction between two atoms or two molecules? For example, I could take two hydrogen atoms, or take another some other thing, for example iron or cobalt or whatever, or two different molecules. We know that the force always goes like 1 over r to the power of 7. If I want to write down the potential energy between two different molecules, the potential goes like 1 over r to the power of 6, force goes like 1 over r to the power of 7. If there were no electrical neutrality, then there would have been a slight excess of the positive charge over the negative charge, or the other way around, then the force would have gone like 1 over r squared. You see, not only do you not see 1 over r square term, you do not see 1 over r cube, 1 over r to the power of 4, 1 over r to the power of 5. You go all the way up to 1 over r to the power of 7, which again strongly hints that the net charge sitting on an atom or a molecule is 0, but it is only the electrons that are moving. The protons inside the nucleus itself is not moving. Therefore, we can conclude that the charges are independent of the state of motion. In saying this, I have actually made use of a very, very remarkable fact implicitly, which I did not state explicitly. Now it is time to state that. That is one of the mysteries of nature, and we shall ask what it is. And that is, when I stated this neutrality, I implicitly assumed that magnitude wise Qp equal to Qe. Qp is the charge carried by the proton, Qe is the charge carried by the electron. Now there is something remarkable about that. What is that? Look at a proton and look at an electron. An electron has a mass which is given by roughly 0.5 MeV by c squared. If I convert it into ordinary units, it is of the order of 10 to the power of minus 31 kilograms. That is what I have. What about a proton? Proton is roughly 2000 times heavier than the mass of the electron. So what shall we say? The mass of the proton is roughly 2000 times mass of the electron. They are two different objects. In fact, I know that electron is a point particle. It has a radius less than 10 to the power of minus 17 centimeters. So let me write that. So the radius of the electron is less than 10 to the power of minus 19 meters, whereas the radius of the proton is of the order of 10 to the power of minus 15 meters. We know that it has a finite size, whereas electron is a point mass. The proton is 2000 times heavier than the electron, whereas the electron is indeed light. In spite of that, there is a great equality between Qp and Qe except for the sign. If this were not so, if the proton had carried a slightly excess charge over the electron, then my atom would not have been neutral and I would not have been able to verify all the statements that I made in the previous page, that there is a van der Waals interaction, it does not depend on the state of the motion, atoms are neutral, molecules are neutral, and so on and so forth. And this is something which has been verified to an enormous accuracy in modern day experiments in high energy physics. And let me write down the numbers for you. How do the numbers look like? So let me construct a ratio R which is given by Qp by Qe. Now Qp and Qe have different signs. Therefore, what I shall do is to take the modulus of them and call it as the ratio R. So what shall we do with this now? We shall ask for the departure of this R from 1. So now I ask, what is the modulus of 1 minus R? Remember, R is nothing but mod Qp by Qe. Modern day physics actually tells you this 1 minus R is less than 10 to the power of minus 21. That is what it says. That is, if you took an assembly of 10 to the power of 21 protons, if you look at an assembly of 10 to the power of 21 electrons, measure the total charge there, measure the total charge here, you are still not able to distinguish any difference between the total charge contained in the two assemblies. This is such a vanishingly tiny number. Notice, I have not even put them less equal to, I have put them less than or equal to. In fact, one can even safely say that mod 1 minus R is less than 10 to the power of minus 21. Maybe it is less than 10 to the power of minus 25, minus 30, minus 40. Future experiments will reveal that, but for our purposes, we can simply say that 1 minus R is identically equal to 0 or R is equal to 1. This, in fact, is one of the surprising mysteries of nature, but it is this fact that allows you, in fact, to verify the charge neutrality of the atoms. Now, when I am speaking of the proton and the electron, we should remember that matter is composed of yet another third object, namely the neutron. What about the neutron? Neutron is again a very funny object. It also has a mass which is roughly 2000 times the mass of the electron. It is slightly heavier than the proton. So, my mass of the neutron is again 2000 times the mass of the electron, and mass of the neutron is slightly greater than mass of the proton, which is the reason neutron can decay into a proton. You know the famous beta decay. Now, if you ask what the charge of the neutron is, then it turns out that the charge of the neutron is equal to 0. That is what we find here. I should also mention the radius of the neutron. The radius of the neutron is also again of the order of a femtometer, 10 to the power of minus 15 meters. Therefore, it is very, very much like a proton. Very close to the proton in its mass, very close to the proton in its radius, but when it comes to charge, it is 0. It is a neutral particle, which is the reason why it was called a neutron and it was discovered by Chadwick, as you all know from your 12th standard. What is the experimental limit on that? If I express the charge of the neutron in terms of the charge of the electron, it is known that Qn is again less than 10 to the power of minus 21 into Qe. Never mind whether you want to ascribe a positive charge or a negative charge, it is less than 10 to the power of minus 21 times that, and therefore we can again safely conclude that Qn is taken to be 0. These are indeed very, very precise limits. Notice, these are only upper limits. We are not saying that the charge of the neutron is 10 to the power of minus 21. We are saying that if at all a neutron has any charge, it is less than 10 to the power of minus 21 times the charge of the electron. Therefore, we are not committing any error, any approximation or any bungling if we safely set Qn is equal to 0. How do I know that Qn is equal to 0? Well, go back to the atoms and look at the same atom constructed out of different isotopes. You have oxygen 16, you have oxygen 18, you have nitrogen 14, you have nitrogen 12. Now, Z is the same for both of them, but the number of neutrons keeps on increasing. Again, we know that the interaction is entirely given by the force between the proton and the electron. The neutron does not play a role. Therefore, that gives you a hint that Qn is equal to 0. Why have I spent so much time discussing the proton, the electron and the neutron which occur in modern physics? The reason for that is plain and simple, and that is the following. All matter that we know of is made of the protons, the neutrons and the electrons. You might become a material science engineer, an electric engineer, an electronics engineer. You are going to deal with matter. Is that okay? Plastics, metals, whatever. All of them are made up of molecules which are made of atoms, and atoms are composed of the protons, the neutrons and the electron. What have we stated just now? We stated that neutron does not have any charge, and the charge of the proton and the electron are precisely the same, with a limit given by 10 to the power of minus 21, which is vanishingly small. And whenever I say that I charged my capacitor, there is a current flowing in a wire. There is a semiconductor which has built up a charge at the interface because of the contact potential or whatever. Whenever we are saying that, we are only accumulating these fundamental charges. They might be enormous in number, never mind about that. There might be about, suppose the total charge is 10 to the power of minus 10 coulombs. The charge of the electron is of the order of 10 to the power of minus 19 coulomb. We know that in terms of the ordinary unit. So even if I have 10 to the power of minus 10 coulombs, I have 10 to the power of 9 electrons which are sitting there, okay? Whatever it might be, all finite charges, all finite currents are actually built out of the basic building blocks, the electrons. And what do we mean by saying that? That means all charges are quantized in the units of the electric charge, which I shall write explicitly. So this is the famous charge quantization. So what does it say? All charges come in units of the charge carried by the electron. Carried by the electron. If you feel like, you can also replace the electron by proton, because they are both the same except for a sign, and this remarkable thing is what is meant by charge quantization. There is yet another very important property of charge, and that is the conservation of charge. That is a detailed topic which we shall take up in the next lecture.